Have you ever stopped to think about how your voice can travel across the entire planet in an instant? Or how a single click can sharpen a blurry photo? Well, it all comes down to this invisible language that powers our modern world: signals and systems. It's the bedrock, the fundamental framework for everything from your smartphone to medical imaging. So let's pull back the curtain and see how it all really works.
So here's our game plan. We're going to break this whole thing down into 5 key parts. We'll start with the signals themselves, then we'll look at the systems that process them. After that, we'll dive into some powerful mathematical tools that make complex problems surprisingly simple, see how the real world gets turned into digital data, and finally, learn how engineers can basically predict the future behavior of any system.
All right, first up, let's jump into the world of signals. You know, at its heart, communication is just about getting information from a source to a destination. And that information, whether it's your voice, a photo, or a stream of data, it needs a way to travel. That vehicle is a signal.
So what is a signal, really? Well, simply put, it's a function that carries information. Think of it like a story being told with numbers, a story about something happening in the physical world. It could be the voltage in a circuit changing from moment to moment, the specific colors of pixels in a photo, or the incredibly complex data that makes up a video you're streaming.
Now, the cool part is that engineers don't have to build every complex signal from scratch. They have this set of basic building blocks, these elementary signals that are kind of like Lego bricks. You've got the unit step, which is basically like flipping a switch to on. The ramp, which is just a steady, constant increase. The impulse, that's a sudden, massive burst of energy. And then you have the more familiar ones, like sine waves and exponential curves that describe everything from radio waves to how money in a bank can grow.
Signals really come in 2 main flavors, and they represent the analog and digital worlds. Continuous time signals are smooth, they're unbroken, defined for every single possible moment in time. Think about the groove on a vinyl record. But discrete time signals, that's the language of computers. They're a sequence of individual snapshots, just taken at specific, separate moments.
And you can see that difference perfectly right here. On the left, you've got that smooth, flowing analog signal. And on the right, its discrete counterpart, just a series of distinct points, or samples. This is the fundamental difference between, say, the continuous sound wave from a guitar string and the sampled data that makes up an MP3 file. Okay, let's move on to section 2. If signals are the information, then systems are the machines that actually do something with that information. They are the signal processors.
You know, the easiest way to think of a system is as a black box. You feed it an input signal, let's say it's a noisy audio recording. The system inside that box applies a specific set of rules, and what comes out is a brand new output signal, like that same audio recording, but now the hiss and crackle have been completely filtered out.
Now, to really understand these black boxes, engineers ask a few key questions to classify them. Is it linear? Basically, if you double the input, do you just get double the output? Is it time invariant? Meaning, does it work the same way today as it did yesterday? Is it causal? So can it only react to things that have already happened? And finally, is it stable? If you give it a reasonable input, are you going to get a reasonable output, or is it just going to spiral out of control? Answering these questions lets you predict exactly how a system will behave. Okay, on to section 3, and this is where things get really, really powerful. We're talking about transforms. This is how engineers take a ridiculously complex problem and just look at it from a completely different angle to find a simple solution.
So here's the challenge. The behavior of a ton of real-world systems, like an electronic circuit or a car's suspension, is described by some pretty complicated math, specifically differential equations. So how on earth do you solve these things to predict what the system will actually do?
Well, the truth is, trying to wrestle with these equations directly in what we call the time domain, which is just looking at how signals change over time, can be incredibly hard. The calculus gets messy, and it's almost impossible to get a clear picture of what the system is truly doing.
But this is where the magic happens. Transforms are a mathematical tool that take those gnarly differential equations from the time domain and turn them into simple algebraic equations in a new frequency domain. All of that painful calculus suddenly becomes basic algebra, which is just way, way easier to solve.
So the 3 main tools in this toolkit are the Fourier, Laplace, and Z-transforms. The Fourier transform is awesome. It's like a prism for signals. It takes a complex wave and breaks it down into all the individual frequencies it's made of. The Laplace transform is the go-to tool for analog systems, helping engineers see how they'll react. And the Z-transform, it does the exact same job, but for the digital world.
This brings us perfectly into Section 4, from continuous to digital. How do we take the smooth, analog reality that's all around us and convert it into the ones and zeros the computers actually understand?
The entire digital world is built on one kind of mind-blowing idea, the sampling theorem. It says that as long as you take snapshots of a signal fast enough, and fast enough means at least twice its highest frequency, you can perfectly rebuild the original signal later on. No information is lost. It's like knowing you can perfectly capture the motion of a helicopter's rotor blades as long as your camera's shutter speed is high enough.
So this process of going from analog to digital, or A to D conversion, it happens in 4 key steps. First, a filter gets rid of any frequencies that are too high to be captured accurately. Second, we sample the signal, which just means we measure its value at regular intervals. Third, each of those measurements is quantized, which is basically just rounding it to the nearest value on a predefined ladder of levels. And finally, each of those levels is encoded into a unique string of ones and zeros.
And this is the actual hardware that makes it happen. The signal comes into a sample and hold circuit. Its whole job is to grab the voltage at one precise instant and just hold it perfectly steady for a fraction of a second, just long enough for the A to D converter next to it to do its job and figure out the right binary code.
All right, time for our final section, predicting system behavior. This is where everything we've talked about comes together, giving engineers an almost uncanny ability to predict how a system will react to, well, to anything. The secret weapon here is something called the impulse response. Imagine you hit a system with a perfect instantaneous burst of energy, that unit impulse we talked about. The way that system rings or vibrates or just reacts over time, that is its impulse response. It's a totally unique signature, like the system's own personal DNA or fingerprint. It completely defines what that system is.
And here's the incredible payoff. If you know a system's fingerprint, its impulse response, you can then predict its exact output for any input signal you can possibly imagine. The mathematical tool that lets you combine the input with the system's fingerprint to reveal the output is called convolution.
Now, convolution can sound a little intimidating, but this table really breaks it down. All it is a process of sliding one signal over the other. At every single step, you just multiply the values that are currently overlapping, and then you add them all up. And by doing that over and over, you build the final output signal one piece at a time.
And this brings it all right into the real world. This diagram here shows a super common digital filter. The input signal comes in, and at each stage it gets multiplied by one of those H values. So, what are those H values? They're literally just the data points from the filter's impulse response, its fingerprint. By carefully choosing that fingerprint, engineers can design a system to do pretty much anything, like boost the bass in your favorite song or sharpen a blurry picture on your phone.
From the electricity in our homes to the data floating in the cloud, our world truly runs on signals and systems. It's this incredible language that lets us describe, analyze, and ultimately build the complex technologies that shape our lives. So the only real question left is, now that we understand this language, what new conversations are we going to start? What are we going to build next?